clanging, rattling, clanking, vibrating, buzzing. Localizing and defining a noise is challenging enough. This becomes even more difficult when garages have to localize these noises in response to a customer complaint. This has not gone unnoticed at AVLD Test, and it is precisely why the test and measurement technology specialist developed the ACAM, the acoustic camera. Simon Schmidt from garageanalyze.de will now show us how exactly it works and the technology that is involved. The centerpiece of the measurement technology is the ACAM, a mobile acoustic camera manufactured by AVLD Test. It is comprised of an 8.1-inch display and has the great feature that the whole camera can be put to mobile use in the workshop just as it is. It has an integrated battery that powers both the tablet as well as the 64 microphones at the rear and the digital camera. In dark spots, you can simply switch on the 4 LEDs to perfectly illuminate the area being recorded. The 64 microphones and the digital camera let you film the acoustics as well as the background and components that are causing the noise. These are joined by additional accessories, such as a practical push button that you can use to carry out measurements. This is an optional accessory that is not always required, but is perfect for starting and stopping measurements if you need to reproduce a noise and you do not have direct access to the camera. The equipment also uses a tripod. This is very practical for carrying out measurements on a passing vehicle, for instance outside in the yard. Or it lets you position the camera. Place the entire measurement technology in front of the engine compartment and use the acoustic camera to record engine noises while you are inside reproducing the noises at the right speed. So you don't necessarily need a second person to help with measurement. You can use the push button and the tripod to position the camera so that you can carry out the noise analysis alone. Headphones are also included. The headphones can be connected to the camera during measurement so that you can listen in to what the camera is filming and recording live from inside the vehicle. Many workshops already have a number of small acoustic measuring devices, such as a stethoscope or a screwdriver, but any analysis with these devices is naturally limited. It is naturally possible to trace a noise while standing in front of the engine, but this ultimately does not let you document the noise. This documentation is made possible by tools such as the ACAM, the acoustic camera, which lets you document noises before repair, as well as during the repair, and then lets you display the results of the documentation and repair to the customer. And it clearly also displays a certain level of expertise, a certain professionalism in your own car dealership. We humans have the ability of using our 2 ears for directional hearing. This means that if we hear the source of a noise, this source is a different distance away from both ears. If I click my fingers here, the noise arrives more quickly at my right ear than at my left ear because my left ear is slightly further away from the source of the noise. And this time difference, this slight delay, is calculated by our brain. It is usually only a matter of microseconds and helps us pin down the source of a noise in a room without having to see it. The functional principle of the acoustic camera is also based on this time difference. In this case, we have 64 digital microphones that acoustically record the sound event. The software then calculates the time difference. At the same time, the digital camera records a visual image of the background from which the noise originates. And these two results, the acoustic as well as the visual recording, are superimposed in an image. This visual image, produced by the digital camera, here in grayscale, is then displayed as a picture-in-picture with the acoustic image, similar to a thermal imaging camera, with different colors depending on the volume, level and position of the source of the noise. And this makes it easy for the user to localize the source of the noise in the area using the tablet's display. Here we have set up a door panel as an example for the topic of interior noise, such as rattling or creaking noises. Creaking noises occur as a result of the stick-slip effect. This refers to the transition between the static and sliding friction of two materials that are often packed tightly together in the door panel for its visual appeal. This requires narrow gaps, so the components are installed side by side. When the vehicle moves, the car body warps, including components such as door panels, the dashboard, and the roof lining. This can lead to slip-stick effects, which are perceived as an irritating rattling or creaking noise in the interior. As long as these noises are relatively easy to detect, or you can influence a part by laying your hand on it, the sources can be found. But it becomes more difficult if you are dealing with very brief crackling noises, as the sound disappears before you have the chance to put a hand anywhere. This is obviously where the acoustic camera is ideal for recording a very brief noise and localizing it on the door panel. We have simulated 3 noises on the door panel. Here, we can choose from different display options. Firstly, the visual image of the digital camera with the superimposed acoustic impressions recorded by the microphones. At the bottom, here, is the sonogram. The sonogram displays the time on the x-axis. Here, the measuring time was 20 seconds. In this case, the measurement was recorded using a ring memory recording, which means that we recorded the last 20 seconds of the noise with the benefit that the camera can continue running the whole time. The camera is stopped as soon as the noise occurs, after which the last 20 seconds is stored. This time can be adjusted between 20 and 120 seconds. The sonogram displays the frequency of the noise over the time. What we see here are different colors. The dark colors, the dark blue, the black, are frequency ranges, parts of the noise that are virtually inaudible to the human ear. And everything that is shown in orange to yellow is our creaking noise that I have deliberately created. This type of crackling creaking noise has a very broadband frequency spectrum, meaning that it contains very low frequency sections, which tend to be more in the lower area, as well as very high frequency sections. This is typical of a very short, jarring noise. The colors that you see here, very dark blue-black tones, is the dynamic range in the noise measurement. Everything that is dark, black and blue are noises that are barely perceptible, as the volume level is very low. And similar to a thermal imaging camera, everything that is shown in orange to yellow are the frequencies that we can hear very well, and which the camera recorded clearly. This means that, as a user, the 20-second measurement lets you clearly see where noises occurred. You can skip to this measuring point, and the visual image above shows where the noise is created on the door panel. The benefit of the camera is that it gives us 50 images per second, so the user can scroll through image by image. And now I hit the area where I moved the door handle and created the noise. And the source of the noise is precisely projected into the image. If I fast forward a bit, we reach the handle movement section. The handle is an area in which noises often occur because two materials are very close together. And the acoustic camera, once again, precisely shows the position of the source of the noise on the door panel. Finally, I tapped on the bottom right of the door panel, and if we play through this section, You can clearly see that the noise is perfectly projected in the image, making it very easy for the user to localize the source in the different positions of a door panel. Here we use the example of a toy car driving on the road. In this case, we want to show that an acoustic camera can also easily localize moving objects and noise sources, and in such high resolution that, in this case, you can see that the wheels that are in contact with the road are creating the rolling noise. And you can even zoom in so far that you can see the difference between the back and front wheel. Vehicle developers place a great deal of importance on ensuring that the vehicle sounds fits the product. For instance, for a sports car, the sound is developed so that the vehicle sounds sporty and robust. Basically, so that it meets the customer's interest and the customer's expectation, while a luxury saloon sounds as smooth and even as possible. A range of different methods are used during development. Developers try to modify the intake as well as the exhaust systems, install external sound actuators, or car body parts, such as a window screen, are deliberately simulated by a sound actuator to simulate an engine noise in the interior. But it is not just the engine noise that is manipulated. The same is true for less important topics, such as the sound of an electric window. The raising and lowering of the window must have an even and full sound. In this case, there should not be any modulating frequencies. The customer should not get the impression that the window motor is struggling, or that the noise it makes indicates that it does not have the power to raise or lower the window. A similar approach is taken to the noise when closing the door. Here, close attention is paid to ensure that the sound of the door closing is muffled and full, that no panel clatters, and that no rattling noises are generated. The aim is for the door sound to reflect the inherent value of the vehicle, which naturally directly influences the customer's impression of quality. Another reason for customer complaints is that in today's vehicles, noises are becoming increasingly difficult to mask. What is masking? Masking is the practice of using loud noises to cover quieter ones. If you look back into the past, engines were very loud, which covered quieter noises, such as the additional coolant pump when idling. These days, vehicles are often in start-stop mode at traffic lights, meaning that the engine is switched off and you hear everything going on around you, fan noises and additional coolant pumps, which would otherwise be masked by the engine noise. And the same is true for electromobility. The drive noise of an electric vehicle is generally quieter than that of a vehicle with a combustion engine, such as when accelerating, for example. Particularly when accelerating, the combustion engine and its drive noise covered or masked a lot of noises. Now that this noise has been eliminated by new technologies, the customer can naturally also hear, and so complain, about quieter noises. The use of measurement technology is ideally suited to professionally analyzing and recording precisely these kinds of quieter noises in the interior so that the source can be identified more quickly. The ACAM not only lets you record the noises, it then also lets you analyze the situation, as is shown in this example of a brake noise in the workshop yard. Let's start by zooming in on the sonogram. You can see that the light-colored areas are the squeaking noises, and you can also clearly see the time at which they occur. It also shows the frequency that is generated, and you can naturally replay the entire scenario. Besides engine noises, which are also reflected, you can see that the source of the noise was detected in the front wheel brake, and both these things are shown in combination. So, you now know whether the front or rear brake system is squeaking. And the second piece of information that is provided is the frequency. The pitch at which the brake system is whistling. This information can also be used to request advice from the car maker, as a brake noise is generated by fluctuations in the friction force between the brake pad and the brake disc. And these fluctuations in the friction force cause the brake system to vibrate. This means that these whistling noises can be generated from the natural frequencies of all brake system components, and, depending on which component enters into this natural frequency, the caliper, the brake pad, or the brake disc, different measures can be defined or different repair suggestions can be provided and developed. Another application of the ACAM is to analyze noises in engines. In this case, we recorded the engine in the workshop at idle speed. And you can now use the acoustic camera to move over the individual components in the engine compartment to once again obtain a clear visual display of which component is emitting this rattling noise. In this case, the high-pressure pump is responsible for the rattling noise that you hear when idling, which is projected onto the image here and is graphically displayed. Here, you can clearly see the leak above the A-pillar at roughly the height of the mirror. These kinds of aerodynamic noises can also enter the vehicle, in which case customers generally complain about the wind noise, the aero acoustics. This usually occurs at higher speeds, if a door seal or a window frame no longer establishes a complete seal, and the aerodynamic noises enter the interior. I now have Jens Dahlheimer, sales manager at AVL D-Test with me. Mr. Dahlheimer, what led to the development of the ACAM? We developed the ACAM together with the premium car maker for mobile use in the workshop. Now we know that acoustic cameras have existed in the industry for quite some time. What distinguishes the ACAM from these industrial applications? It is small and durable and suitable for day-to-day use in the workshop. Does this mean that it has been specifically designed for specific workshops, or can it be used by any workshop? It can be used by any workshop that has to deal with noise formation issues. Noises will continue to play an ever-increasing role in the automotive industry, especially in view of electromobility, because they are perceived completely differently. The ACAM was built specifically for this purpose.